Ladies and gentlemen, welcome to tonight's occasion. Thank you all for coming out on a school night. Before we begin, I'd just like to thank the other societies for their previous efforts in hosting our previous 4 societies meetings, which is an annual event. That includes the Royal Society of New South Wales, the Engineers Australia Nuclear Engineering Panel, and the Australian Institute of Energy. My name is Dr. Mark Ho. I am a nuclear engineer. Day job is working at ANSTO. However, all comments, etc. for myself tonight, all my own. And I'm also the ANA president currently. Tonight, we are treated to an update of the state of R&D in fusion, which is of immense interest, judging by the crowd, by one of our very own Professor Matthew Hull from the ANU. Currently, a professor at the ANU's Mathematical Science Institute and School of Computing. Professor Hull holds degrees in physics, mathematics, and electrical engineering, and completed his PhD on plasma centrifuge physics at the University of Sydney. In 2001 and 2002, Matthew worked at the UK Atomic Energy Authority on the innovative spherical tokamak concept. Then, in 2003 and 2004, he worked at the University of Sydney on space plasma physics, so low-density plasma, I'm guessing. And then, since 2005, he worked with Professor Dewar at the Plasma Physics Modelling Group at ANU, which Professor Hull now leads. Professor Hull is the Australian member of the International Fusion Research Council of the IAEA and is part of the Board of Editors for plasma physics and controlled fusion. Professor Hull is also the inaugural chair of the Australian ITER Forum, a consortium of scientists and engineers from universities, research labs, private industry, the greater public, which seeks to promote fusion science. So please join me in welcoming Professor Matthew Hull.
Thank you so much for the introduction. I'll see if I can find my talk. My computer's not gone to sleep, which it might have. Right. Make sure that works. Great. So thank you again. So I was invited a little while ago to give this talk, and so thank you on behalf of the 4 societies for doing that. This talk is kind of a whirlwind talk covering what fusion is, talking about the current state of technology, and then touching largely, or touching to a large degree, on private sector investments, which are changing the sector at present. And then talk about perhaps what the future might hold. So let's advance. So fusion is the process that powers the sun, the stars, and nearly all life. So if I look at the sun, the process that powers the sun is the 4 protons coming together. That should be 4 heliums, not 4. 2 plus 2 neutrinos and 2 positrons, and produces 26.2 MeV. So this process has powered the sun for billions of years. Because I'm actually walking away from the mic, which I was told not to do. Apologies. Yeah, what? I just use this. That's better because, yeah, I tend to walk away from the mic. So anyway, the point is that fusion is the process that powers the sun and has done so for 4.6 billion years and will burn for another about 5 billion years. So the conclusion immediately from this slide is the natural world is sustainable and solar fusion powered. That's immediately obvious. Fusion also formed most of the elements in the universe. So helium and hydrogen were formed primarily in the Big Bang fusion of gluon plasma. Lithium, beryllium, and boron are formed by cosmic ray spallation at very high energies. Most of the elements, up to iron, are formed by stellar processes during solar evolution, and atoms or elements beyond iron are created mainly by supernova and merging stars. So fusion, the process of fusion is responsible not only for all life, it's also responsible for all the elements in the universe, or just about all of them. So whilst the sun is sustainable and the world is natural powered, civilization is clearly not. Civilization is powered primarily by fossil fuels, so this shows the fossil fuel burning or fossil fuel energy from 1800 to the present. And if you overlay climate change or the rise in sea temperature on the Earth's atmosphere, it very, very strongly correlates with that figure. And what you can see at present is that nearly, 83% are coming from fossil and biofuels. I put them together because they're still producing CO2. It may be a biofuel, but it's still producing CO2. 13.2% and growing from renewables, which is great, and a small contribution from nuclear. So you might look at this and say, well, Australia's a small country, why should we care? Well, why can't we just ignore the whole problem? Well, we are the world's largest exporter of coal by export value. We're the world's third largest fossil fuel exporter. Our emissions are the highest per capita in the OECD, and we are responsible for 4.5% of global emissions, 80% of which is overseas. So this is big. We have a massive environmental footprint. So we have some responsibility, I think, to do something about it. The final point is that greenhouse gas emissions don't respect national borders. The problem is truly global. And we are doing something about it. We're massively increasing the uptake of renewables. So, and in that context, you could ask, what is the role of nuclear, either fission or fusion? If you do some simple calculations, you can work out relatively quickly that solar power could supply all of Earth's needs if storage and transmission are solved. You can compute that an area which is enormous, but if you take the solar PV output in Alice Springs, you can work out that a 600 by 600 kilometre grid would meet the entire global energy needs of the Earth. However, there is a big problem here, and the first of all is that transmission and storage are not solved problems. And the second problem, even if they were solved, energy security remains a significant geopolitical driver. This is to a large degree why Europe has invested so substantially in this technology. They're terrified of Russia putting their foot on the gas line, which they do fairly routinely. So this is a concern for the planet. If you want to solve global energy and you want to solve CO2, you need a global solution. And so nuclear, either fusion or fission, will be part of that. A fusion power plant, and a fission for that matter, is about 1 to 2 gigawatt electric. And the immediate conclusion you can draw from this, if you look at the area that's required, that it's also the most land-efficient, large-scale energy source available. And that's why France, Japan, and South Korea, amongst others, fit huge energy output into small countries, and nuclear pairs extremely well with renewables if land, material, or transmission is constrained. Regardless of what we do, global capacity is on track to double by 2050. So the message I want to leave in the first instance of this talk is that whilst Australia is blessed with lots of renewables, civilization needs nuclear power, and the sector will only grow. This creates opportunities for Australia, not only in fission, but also, I think, in fusion. So let's talk a bit about what fission, fusion, and combustion is. I've introduced what fusion is. It's the combination of light isotopes to form something heavier. The first reaction that was discovered was, in fact, by Sir Mark Oliphant in Cambridge. He was Australian, but he did the work in Cambridge. And that produces helium-4 and an energetic neutron. So this produces an energy gain of 450 to 1. So this is deuterium plus tritium goes to an energetic alpha plus the neutron. There are a whole class of other reactions here I've put in a less shaded colour because this reaction, as we'll see later, is the highest cross-section. If you're going to initiate any fusion reaction, you're going to initiate that one first. But the other reactions are DD, which produces a neutron. There's another reaction that is aneutronic. There is deuterium helium-3. This is where you get the idea of mining on the moon for helium-3. And there's proton-boron, which is the only aneutronic branch, only truly aneutronic branch, because as soon as you introduce deuterium, it produces neutrons. All of these things have millions of MeV. If you then include fission, so fission is fragmentation of something heavier into something lighter, that produces much more energy in total, but about a factor of 4 less per unit mass relative to fusion of DT. All of these things have millions of times more energy than coal. So these are very energy-dense reactions. So the big idea of nuclear generally, and certainly for fusion, is that it uses small amounts of resource for big energy production. So you can work out that the amount of deuterium in a bathtub plus the amount of lithium in a laptop, if you convert it to tritium, would be enough to power a person for 30 years. the attraction is that on Earth it could produce large-scale electricity production. Deuterium, as you'll see in a moment, is essentially limitless fuel. There are no greenhouse gases because the process doesn't involve construction or creation of greenhouse gases. It is intrinsically safe. Even if you slammed a 747 into it, the amount of tritium that would be released is at background levels at the site perimeter. Tritium's not nice, so the people inside the facility might be affected, but at site levels, at the backgrounds, at the edge of the site, it would not be a concern to the public. There is no long-lived radioactive waste either. And the reason why is because the process of reaction aren't radioactive. There is a problem with the neutron, because the neutron is very energetic. That can impact another material and then activate that. So it does generate low-level volume of radioactive waste and low-level in time. And so the time frame for recovery of that radioactive waste is about a year. And of course, if you use aneutronic fusion, there's virtually none, because the process is aneutronic, doesn't involve a neutron at all. So let's look at the fuels available. So I've introduced the process. So nearly, when you quote relative abundances, it's always relative to hydrogen, because nearly the entire universe is hydrogen. So for every hydrogen, every 6,000 hydrogen atoms, there's one deuterium. So if you try and burn this DD reaction and look at how long you could sustain life for, it's like 10 times the age of the universe. This is truly limitless. If you burn the DT reaction, tritium has a half-life of 12.5 years, so it effectively doesn't exist in nature at all. You have to activate it, and you can do that by activating lithium by either two channels from lithium-6 or lithium-7. So then if you look at the concentration on Earth, for every 10 to the 6 hydrogen atoms, there's one lithium. And if you ask the question of how long could DT power Earth for at 20 terawatts continuous power, it's about 10 to the 4 years. If you look at the whole solar system, well, they're stupidly big numbers. In the case of deuterium helium, this is the attraction. Several films have been made about this, of mining the moon for helium. If you look at the amount of supply of helium on Earth, it would last like weeks if we were to burn this all, burn all of this. On the moon, there's much more. It would last about 1,000 years or so. But these numbers are still relatively small by comparison to these other numbers. And if you're powered by the proton-boron chain, it's also in millions of years. So the conclusion from this is that each of these, certainly this cycle and that cycle, are effectively inexhaustible, and this cycle is mostly inexhaustible, particularly if you access lithium more broadly than just in the crust of the Earth. So, okay, I've introduced what the fusion process is, how long you could supply Earth for. How do I achieve this reaction? So I've got two particles that are going to be like-charged. I need to bring them sufficiently close to overcome their Coulomb repulsion to allow the electrostatic, the strong nuclear force to take over, and for the atoms to bind. So I can do this in lots of different ways. I can do this even in a small device about this big with a pyroelectric crystal. So you can apply heat to a pyroelectric crystal, generate a large potential drop across this, and accelerate deuteriums into a target, and you can generate neutrons. This doesn't scale to produce power, but you can certainly generate neutrons that way. You can also have a muon catalysis. So muons are particles that come out of a nuclear reactor. They have a lifetime of milliseconds or microseconds. Actually, I think it's microseconds. They do accelerate the probability of reaction, but the amount of flux that comes out of them is tiny, and they last transiently. You can do it by inertial confinement. And so in this case, what you're doing is you're firing a whole bunch of lasers down to a uniform target or a hole ram, and you're lifting the temperature of this hole ram to hundreds of millions of degrees to allow the fusion process to occur and to burn up the entire material inside the chamber. So this process, there is still confinement going on because it's confinement to burn up all the material, but it's essentially a pulse detonation experiment where you blow up the pulse, you blow up the target. And so this National Ignition Facility that was built in the US, its primary purpose is not to do energy science. Its primary raison d'etre is to maintain the US nuclear capability in terms of weapon capability under a comprehensive test ban treaty. That's the reason why that facility exists. But nonetheless, there is a path. If you can go from a couple of pulses per week to 10 pulses a second to turn that into electricity. And the confinement path that I'm going to talk about mostly is either gravitational, we know this works, electrostatic or electromagnetic, or a type of polyworld configuration. There's some experts in the room, including Joe Kashan, who has, or will have a startup company in this space, and toroidal magnetic confinement, which I'm going to devote much of the talk on. So I've talked about how do I achieve fusion. What about fusion power? So I need to produce this strong electrostatic repulsion, but I need confinement and I need power gain. Otherwise, all I'm going to get is an interesting physics experiment. So I need to maximize this temperature to exceed the Coulomb barrier. I need to maximize the density, which is proportional to energy yield, and I want to maximize this energy confinement parameter. Where this is really coming from is a heat balance. It's basically saying the fusion power has to be greater than the heat loss. And if I look at this picture, well, there's two things to note. First of all, these things are intuitive. You could ask the question, what is an energy confinement time? Well, if I have a jug and heat it up, it's the characteristic amount of time it takes for that jug to cool down. So it's a confinement. It's an insulation parameter, if you like. And on the right, you can see this thermal collision cross-section of reaction as a function of center of mass energy. So this comes from nuclear science experiments with accelerators, and you can work out this is the probability of a fusion reaction as a function of central mass of energy. And you can see the one that it has by and far the highest probability is the DT reaction. So the DT reaction peaks at around about 600 million degrees centigrade, and it's several orders of magnitude above DD and everything else. Unless you go to very high temperatures, getting up to, I don't know, 250 keV, or even 600 keV, where the deuterium helium-3 and proton-boron cross-section is higher. But these are very much higher temperatures. So the easiest one to initiate, if you can initiate anything on Earth, is the DT reaction. It turns out this cross-section, ND tau E, has a minimum at Ti equals 14 keV, which is about 150 million degrees centigrade. So it's not quite so challenging. These are insane temperatures. This is about 10 times hotter than the core of the sun. The sun works not because it's hot, but because it's incredibly dense and incredibly big, as we'll see later. So, okay, so at these very high temperatures, the gas exists in a plasma state. So what's a plasma state? If I have if I apply a magnetic field in this room, not much is going to happen because the electrons and ions, the electrons are all bound to the ions, so it's chargeless, unless you have a pacemaker. But if I strip off the electrons and the ions and apply a magnetic field, they'll start gyrating around the field lines because there's a J cross B force, or a V cross B force in particular. So that's what a plasma is. It's a soup of charged particles that will respond to an electric and magnetic field. Nearly the entire visible universe is in this state. I stress visible universe for the physicists in the room because there's a lot of the universe we don't see in dark matter, but most of the universe that we see is in a plasma state. And on Earth, it's normally seen as either lightning, the sun, never look at the sun, or Tromsø. So I was very fortunate to go to Tromsø earlier this year. These are pictures I took of the aurora borealis, and it was quite incredible to watch, including one I took from the plane. So that was lots of fun. I can recommend that as an activity. Okay, so I've talked about what the conditions I need. Now I need to talk about how I'm going to get this thing to be both incredibly hot and confined. So magnetic fields cause particles to spiral around field lines. Particles are lost to the vessel walls, but only by slow diffusion across the field. So if I apply this strong magnetic field, the charged particles spiral around the field. The charged-less particles with the neutrons go straight out of the device. They heat the walls. That's how I'm getting power out of it. If I make this a straight device, what will happen is the plasma will just fall out of the ends. So you'll have fairly high losses. So the simplest mechanism to try and avoid that is to close the configuration back in itself, apply a strong guide field and a large current to cause the field to twist. And once you do that, you'll end up with a magnetic bottle that confines the plasma. So what's the component? That's called a tokamak. So what are the components of a tokamak? The reason why I'm focusing on this is because this is the primary path, this is the primary research path of the entire fusion program. The components of a tokamak comprise the vessel chamber, in which I introduce a gas that's going to be ionized. I then apply some toroidal field limbs around this, which produce this really strong guide field in the long way around the machine, toroidal direction. I then apply a solenoid, and the purpose of this solenoid is to produce a large field that goes around this iron yoke, and the point of it is to induce a current that goes around in the toroidal direction around the machine, which then produces this poloidally confining field. And to do that, and to add to that, I then add some shaping coils to shape the field. So what I end up with is a magnetic bottle, which is comprised of largely external field produced by primarily the toroidal field limbs and some shaping field and the internal current, which produces the poloidal field. So if I follow the field, it doesn't go around just in a toroidal direction, it twists. It goes a large chunk of it goes in the toroidal direction, but it also twists in the poloidal direction. And it turns out that in that configuration, if I follow a field line, it will always lie on a flux surface. It will lie on a surface. So if I won't use the word poincaré, but if I follow the field line, it will puncture that surface and will lie on one of these lines continuously. In each of these lines, first of all, if the field is very strong, the gyration will be very tiny around it. Secondly, they form these flux surfaces. The next point is that these flux surfaces are thermally insulated in some sense. The cross diffusion across them is very low. So the surface can support a pressure gradient, and by having lots of these surfaces, I can then produce a core peak in the center of the plasma. That's how I get it to, that's how I use the magnetic bottle as a configuration to get hot. Now I have to heat it. Now I have to heat it to 150 million degrees centigrade. How am I going to do that? Well, a combination of ohmic heating, so if I pass wire through a current through a wire, it'll heat up. That's ohmic heating. That peaks out at around about 2 keV or so. What I also need to do is supplement that with electromagnetic heating, so a microwave effectively, which is coupling power from the antenna to the plasma and heating it. An additional path that's used particularly for current experiments and AEDT is neutral beam injection. So this literally in some sense is billiard ball physics, because you have an ion source which goes through an accelerator, then you have a neutralizer, so you have charge-less particles that are very energetic. They don't see the magnetic field, they pass straight into the plasma, they undergo this charge exchange reaction, so they undergo a collision cross-section reaction, and you end up with a fast particle population inside the plasma. And of course, ideally you get significant fusion yield as well, which is also heating the plasma. Okay, so that's how I get it hot. Now I need to know something about how this confinement time scales with size. So this picture shows this triple product that I mentioned as a function of central ion temperature, and there's a whole bunch of data on this. It has some data from inertial confinement as well. So when physicists don't really understand the parameter dependence of something, what they can often do is look at how it scales. This is not a great solution, but empirically, you might be able to get some idea about how the confinement might scale if you increase the field strength, if you increase the current, or increase the size. And you can see right here that has a massive size dependence. So this confinement significantly improves if you make the device big. And that's why machines like the Jet European Taurus are relatively large. So to date, we've been able to produce just below power gain of unity. So these are curves, these contours that you can't see very well, but you can see these ones up here. These are power gain thresholds going from 1 to 2 to 10 to infinity. ITER will produce this burning regime where this power gain is a factor of 5. Why a factor of 5? Well, it's simply because if you look at the total energy output, 3.5 plus 14.1 and divide by 3.5, you get a factor of 5. And the point being is at that point, the auxiliary heating is less than the external heating, less than the fusion power that's been put into the plasma. I'll try and continue despite the distraction. And of course, what you ideally want to do is turn off all these heating sources together and you end up with ignition. So you're trying to light a fire when it's raining, if you like. What you wanted to do is get sufficiently hot, and then it doesn't matter if it's raining anymore, it will just burn. What's new? So there have been some new developments in this. So in 2022, the joint European Taurus was able to demonstrate very high energy of very high confinement for a long time. So these were the earlier experiments which produced that power gain of 1. But since then, they had been doing some experiments that produced a long pulse length with a large amount of stored energy, which is inside the plasma. So these confirmed predictions of plasma behavior and advanced the design of, or advanced the development of ITER high-performance scenarios, which I'll discuss in a second. The other advancement was that this facility that I mentioned, this laser facility, was able to demonstrate ignition. And what I mean by that was that they were able to lift the temperature of the capsule to the point where the entire DT fusion fuel was internally consumed. So all of the fusion materials were consumed. So in previous experiments, they hadn't been able to do that. So they accessed for the first time this burning plasma regime where the capsule was not only self-heated, it completely destroyed itself because it consumed the entire fuel. So what's the next step along this ITER path? I mentioned before that these experiments, if I go back to this picture over here, you can see that these experiments are coming close to break even. What I want to do is try and explore this burning regime. Well, that's exactly what ITER is intending to do. So this ITER experiment, formerly known as the International Thermonuclear Experimental Reactor, which they realized is actually also Latin for the way, or the path, and they like that better, so that's what it's now called. They deleted the acronym. But the idea is to achieve a deuterium-tritium plasma in which fusion conditions are sustained mostly by internal heating. This is this burning plasma regime I talked about. Generate 500 megawatts of fusion power for long pulses. So long pulse or continuous operation is critical, I think, if you're going to produce large-scale power. It was intended to contribute to the demonstration of integrated operation of technologies for a fusion power plant, test tritium breeding, and also demonstrate the safety characteristics of a fusion device. That's the idea. Here's the snapshot. So the facility came together, or the project, actually the project goes back to, it was a Gorbachev-Reagan summit that was launched many years ago, and the project was meant to be a world peace scientific project trying to advance energy. It's taken a number of years for ITER to both be formalized as an entity and for construction to start. A site was selected, I think in 2006 in Cadarache, following intense competition. It's designed to produce, as I said, this power gain of greater than 10, central core temperature approaching 150 million degrees, and it's a growing consortium. Here's a person for reference down here. The other comment I will make, which will, actually I'll leave that for a second. There are also collaboration agreements, not only with the International Atomic Energy Agency and the Principality of Monaco and CERN, but crucially Australia. So Australia is a very small player in a fusion landscape, but they recognised our technical capability and agreed to a technical cooperation agreement. There was meant to be a subsequent injection of funding, which didn't happen from the Australian government, but the fact that they recognised Australia has technical capability in this space and were able to make Australia a partner without paying the huge cost of membership is a pretty good testament to Australian science. And I'd also like to thank ANSTO for recognising that and also pursuing that on behalf of the Australian science landscape. I guess partly inspired that, others had a similar idea like Kazakhstan. Unlike Australia, they are pouring large amounts of money into this space. So let's look at ITER in detail. So I mentioned it produces 500 megawatts of power. It's a large device. Here's a person for scale. So if you look at the volume in this, it's about a third of the size of an Olympic swimming pool. It's based on niobium tin superconductors. So to produce these superconducting fields, which are about 5.3 Tesla, the whole internal cryostat has to be cooled down to liquid helium. So it's going from 4 Kelvin to 150 million degrees in the center. It's got 300 lightning bolts of current flowing around it and auxiliary heating of about 73 megawatts. So this is a big facility. And it is now being built in France. And indeed, I've been there multiple times. I was there in May last year. I was also there in December. This is now immediately dated because Richard Garrett showed me that they've now installed 5 sector modules as of today. So they are now rapidly putting the internal components together of the tokamak itself. ITER is a big science project, and it has had its fair share of delays. So I mentioned the site was selected early 2000s, and then was constructed they began the site at Cadarache. It's had a number of different challenges, partly due to project management and scope challenges. The first, because of the agreement, the first two Director Generals were required to be Japanese. Japanese business is conducted very differently to business in Europe, so this created some difficulties in trying to implement. And also, Aikida was not even a scientist. Aikida was a diplomat. So the first person in this job knew nothing about science at all. So there were some initial challenges associated with it. There was also a problem in the way that AEDT was procured, because all of these different partners were putting in large amounts of money. They wanted to make sure that they're getting something out of industry for it. So rather than having one magnet winding facility that might wind 9 different magnets, they distributed it across 8 different manufacturers. And when you do that, and you require the machine to fit together, there's a pretty high likelihood that they've used slightly different dimensions. And indeed, when they started putting it together, they realized that, in fact, it doesn't fit. So they had to do retrospective welding, and in some cases, shave off pieces of metal to get the machine to fit together. So this is a problem of how you do science at large integration with many different partners. A better model would have been to give all the money to ITER and let them manage it, rather than doing this distributed approach. But it was an experiment not only in science, but also in how to do science. In the mid-20s, Bernard Bigot came along and pursued a very aggressive timeline and was able to bring the project kind of back on scope, although he ended up dying in office. Literally, he died in office because he put so much effort into this. He had cancer at the time, and unfortunately, he didn't quite pass away in his office, but they had to take him out a week before he passed away because he was so committed to his job. We have a new Director General, and so that new Director General has created a new time plan, which is now not only on track, but it's actually ahead of schedule. So that's the first time it has been able to do something which is ahead of schedule. They're constructing the device. The first plasma will be just after 2034. They have a research phase, which will last several years. Why do you have a research phase before DT operation? Well, it's because as soon as you put deuterium in the machine, it's activated by this DD reaction channel. So the first experiments will be hydrogen or argon or something which doesn't involve deuterium. Once you put deuterium in, the machine is activated. And then from 2039 onwards, DT operation. The projected cost is around about 20 to 25 billion US dollars. But it's not alone. So if you look at there are some examples of projects that are within scope and within time. Opal was a great example. But there are lots of first-of-a-kind experiments that are over scope and over time. A classic example is the James Webb Telescope, which was designed in 1996, aimed for launch in 2007, but wasn't actually launched until 2021 at a final cost of 10 times the initial outlay. The Joint Strike Fighter, initial design work in 2001, with full production rate scheduled 2015, didn't occur to 2024, and the lifetime cost is nearly $2 trillion US dollars. That's a lot of money for a device solely intended to kill people, but hey, I'm a pacifist. And the Olkiluoto, I don't think I pronounced that correctly, nuclear power plant in Finland, which started in 2005, scheduled operation in 2009 at 3.2 billion, commercial operation in 2023 at a final cost of 11 billion euro. So I've introduced ITER, but ITER is not a power plant. So the question is, let's suppose I build a machine, how am I going to get the power out? How am I generating electricity? So what you're doing is you're coupling a 21st century thermodynamic engine, if you like, or a thermodynamic source to a steam turbine. So it's 21st century, it meets James Watt. You've got a steam turbine here, which is being generated by a heat exchanger. And so much of my work works at looking at the very complicated nonlinear plasma physics and how you control this incredibly hot burning plasma physics regime. There are other challenges. One challenge is that hasn't really even been addressed is that these neutrons come out at very high energy. They come out at 14 MeV. I need to manufacture tritium. But to manufacture tritium, the neutrons have to be slowed down to thermal speeds. They need to be at room temperature, effectively. So I need to put a meter shielding of moderator of lithium to slow the neutrons down sufficiently so that they will produce tritium. There are lots of other emergent challenges, nuclear technology, such as isotope rehandling, remote handling, because the whole device is in an activated environment, and material science for the first wall. I haven't talked about that, but there is part of the plasma that has extremely high heat flux, and I need to develop materials or use new materials that might be able to handle that extremely high heat flux. So that's what a reactor might look like. You could ask the question, has someone done economic studies on this? Sure. There have been economic studies within Europe which looked at what a demonstration power plant might look like. And I put this here not necessarily to say I believe these numbers, but I put this down to say, give an indication of what the scale of the machine is that would generate power, according to this tokamak concept, and how much, so what the total electric power is to the grid, which is about a bit less than a gigawatt. The reason why it's much larger than that in gross electric power is that it takes a fair amount of energy to operate the machine in the first place. So the amount of self-consumption is quite large. And if you look at the breakdown of construction costs, there is a very large chunk in the magnets. There is also a very large chunk well, actually the cryogenic systems are not that large, but the operating costs of the cryogenic systems are quite large. So if you can reduce the cryogenic cost by making it high temperature, rather than cooling it down to liquid helium, you can reduce the cost of electricity to the grid. So let's talk about what a tokamak reactor design might be. And so the main point I want to make is that these numbers haven't been plucked out of thin air. They're determined by engineering, nuclear and physics constraints of a machine. So here's a machine with a cross-section showing this major radius, which is the size of it, this minor radius, this toroidal field limb, blanket, the blanket, and the plasma in yellow. So if I make the plasma too elongated in this direction, it's unstable. That puts a limit on the elongation. As I said, I need a large amount of, I need a large moderator region to get the lithium to slow down to breed tritium. That produces a width of about 1 meter. If I need to make sure that my infrastructure or the support vessels can handle the neutron wall loading. And if I make a choice of this aspect ratio A on R, it basically determines the size of the machine almost immediately. So that's even without much physics going into it. I haven't even put much physics constraints into the machine. The physics constraints largely comes with this energy confinement time, which I mentioned increases with B. So this tells me that I want to try and maximize that field strength. At the time that AEDT was constructed, niobium tin was the obvious superconductor. That's why it was selected. The field strength limit is about 6.8 Tesla. And so a machine based on this tokamak design reactor concept would have a field of about 6.8 Tesla on axis. The coil windings, I've got this huge current flowing around the machine, 300 lightning bolts of current. I've got these very strong fields. So there's very strong J cross B forces that can be exerted on the magnets. So I need the coil, I need the support limbs to be sufficiently strong that they don't disrupt or rip off the wall, literally. And so that tells me what I need, basically what the width of these winding coils need to be in order to sustain both that J cross B limit and also the curvature or the winding of the coils themselves. This triple product I mentioned has a peak at 14 keV. That's set by the collision cross-section. So this is atomic physics, or nuclear physics really, that's determining that entire value. If I assume that I have, that the fusion power is producing electric power with a thermal efficiency of basically the Stirling engine, 0.4, that produces a central pressure of about 8 atmospheres. I then use the ideal gas equation, which tells me what the core density of the machine is. So it's quite diffuse relative to air. So the density of air is 10 to the 25, the density of diamond is 10 to the 29, and the density of the core of the sun is 10 to the 31, which is about 150 times the density of lead. So the sun is incredibly dense and incredibly big, and those two reasons alone are the reason why it's able to generate a large amount of fusion power. Oh, I meant iron. So the other comment I would make is that I need to ensure that the alpha particle losses, the self-heating is greater than the plasma losses. That tells me what the current is of the machine. And I need in steady state for the machine to be ohmic. So this large current that I talked about, I mentioned I had to have this inductor drive, this central solenoid, to produce that current. I can't have that in an operating machine because it's a one-way transformer. I can't swing it the other way. So I need to have the entire current produced by a combination of current drive, which is RF power that I couple to the machine, and what's known as this bootstrap fraction, which is this self-generated current by pressure gradients. So those are the requirements that I have to make a power plant out of a tokamak reactor concept. And if I stare at this immediately, this describes most of the ITER choices. This is why ITER is the scale it is. It's not producing electric power. It doesn't have a blanket. It fails miserably, well, not miserably, but it fails on the bootstrap fraction. This is not large enough. So ITER there is a challenge with most of the tokamak line in the bootstrap fraction of lifting that to the point where you would have sufficient current in the machine. If you then say, well, what can I relax? How can I change the constraints on this? Well, maybe I might choose a different choice of superconductor. So superconductors came along and improved, and there were these relatively high temperature, I can't even pronounce that properly, Rebco high temperature superconducting tapes, which are superconducting at about 70 Kelvin. And so that both reduces the cryogenic cost, but it also means I can increase the field strength significantly. And the field strength, because tau E increases with B, if I make the field strength stronger, I'll get improved confinement. Another thing I could do is change this aspect ratio. So this aspect ratio is a large reason, or a large chunk of what the UK's activity is, by changing that aspect ratio to make it rather than a large donut, more like a cored apple, that creates both this spherical tokamak consideration, and I'll talk about this about later, this spherical tokamak electricity device that the UK is now investing in. The final thing I could do is just relax the whole concept of a tokamak, at least in magnetic confinement. So I mentioned the tokamak has this axisymmetry and this very large amount of current flowing through it. I could relax that assumption and instead make a device that is twisted in the toroidal direction. And if I do that, it produces this other class of machine known as a stellarator. There are some good examples of this, the Wendelstein 7X experiment that I'll talk about in a moment. And in this consideration, the machine is intrinsically steady state because it has no ohmic current drive. So this is confinement with a twist. So what I do in this is in a tokamak field, you need helicity in order to avoid charge separation. That's created by an internal current. In a stellarator, you do that by twisting the field coils. You need some twist in the machine. So this eliminates disruptive current-driven instabilities, but transforms the problem to a field coil construction. So this is the experiment, the W7X, a German reunification project that's been built, a €1 billion project that was started in construction in 2000. And this is Chancellor Merkel opening the facility in 2016. And the idea of this was to try and exploit what would happen if you computationally optimize the device for low neoclassical transport, low current, and good stability. So that's been churning out some fantastic results since it's been opened. You can do better than that. So the parameter space of optimized stellarators is vast. So this Simon's collaboration that I've been involved with through Princeton University and also a number of other universities was attempting to create and exploit an effective mathematical computational framework for the design of stellarators with hidden symmetries. And the point is that this good flux surfaces I talked about, that's guaranteed in a tokamak, but it's not guaranteed in a stellarator. And these other properties are not automatic either. They're not guaranteed. So what I need to be able to do is I want to be able to have a complex computational simulation that optimizes all of these configurations. And if you do that, you can work out that the first of all, the point is that this parameter space of optimized configurations is vast. Once I relax toroidal symmetry, the whole class of possible configurations is much larger than that of a tokamak. Here's an example that Matt Landerman from the US has constructed, which is a quasi-axisymmetric configuration with good energetic particle confinement and a self-consistent bootstrap fraction. So this involves quite a lot of complex mathematics and a large amount of computational simulation to try and find optimal configurations. Okay, what are some of the potential game changers for fusion? So I've talked about this. I talked about superconductor magnet technology, higher field strength, lower cryogenic cost. What I haven't really talked about is integrated modelling. There has been significant advance in computational understanding, both mathematics and computational understanding, of how the plasma behaves, and has been verified to existing experiments. So that's a game changer in the sense we understand how the plasma is behaving a lot better than what we used to. What I haven't talked about is AI surrogate modelling control. AI for science is changing much of the scientific landscape. Here's an example of a collaboration with DeepMind, in which some collaborators and some colleagues in Switzerland were able to construct what's called a physics-inspired neural network, which was implemented as a control policy to control the shape of TCV, a tokamak that was there. So control is a big deal for tokamaks because you have to control the current quite precisely for the configuration. So if you can find a better way of doing this than simple proportional integral derivative control, which is classical engineering, that would be a significant boost. Design optimization I talked about. Advanced diverter materials I haven't really talked about, but I did say that there was a high heat flux on the footprint down here, and that very high heat flux requires materials that can handle extreme conditions. Radiation-resistant structural materials, as soon as I put a deuterium into the machine, it's going to produce neutrons and it is going to activate over time part of the facility. So I need to design the material ideally from something which is radiation resistant. There have been some recent optimism generated by both the ignition and the jet record stored energy shots. The other drivers are increased urgency of climate action and a wave of capital from tech billionaires. And this is a good point to transition to the private sector. So I've introduced what fusion is and talked about much of the pathway through toroidal magnetic confinement, and I've talked about what some of the potential game changers are. Let's look at the private sector. So the private sector has, this chart shows the number of companies since 1985 up to the present. It has really ramped up significantly over time. There are now, this is a report taken from the middle of last year. At that time, there were nearly, I don't know, slightly over 50 companies, the majority of which are in the USA. There's about 12 companies in Europe, 8 in Asia, and 4 of the rest of the world, one of which is here, HB11, and one of which is in New Zealand, which I'll talk a bit about later, OpenStar. How much money have they been able to attract? So the cumulative investment now exceeds $10 billion. So at that time, in July, they had attracted $9.7 billion. There's been a lot more money that has come in since then. In particular, Trump announced a merger of his company, Trump Media, with TAE Systems and injected another $300 million, which immediately takes that above 10 billion. But there has been other investment as well. And if you look at where much of that money is going, most of it's going into magnetic confinement, nearly half of it. About 11 of those companies, but perhaps less than a fifth or so, are going into inertial confinement, and the rest are a combination of different techniques. And this just shows the growth in some of those companies. I think Pacific Fusion is based in California, so it's not based in the middle of the Pacific Ocean. Commonwealth Fusion, of which the largest is Commonwealth Fusion Systems. So this is a spin-off from the Massachusetts Institute of Technology in 2018. So they intend to commercialize fusion energy rapidly using high temperature or high field tokamak technology, which is high temperature superconductors with advanced materials. And what they're constructing in the first instance, which they're constructing now, is a conventional aspect ratio device, which uses this DT cycle, but it's high field strength. So if ITER has a field strength of about 5.3 Tesla, this is over double that on the central magnetic axis. The current is a bit less at 8.7 mega amps. What they're aiming to do is they're not aiming for Q of greater than 5 or Q of greater than 10. They're aiming for a power gain of greater than 2 with a fusion power between 50 and 140 megawatts. And they have a pulse length of 10 seconds. So it's not aiming for hours of operation. So it's a different class of experiment than ITER. It's nowhere near as ambitious, but it is claiming to do net energy power gain and it is aiming to produce some fusion power. The next step of that experiment is, their next step is this first commercial power plant that they envisage building. Here's a comparison of a person for scale again. It's a much larger device. The field strength is not quite as strong, but it is aiming to produce a 200 megawatt electric device with 500 megawatts of thermal, continuous operation. They claim this bootstrap of 63%. I know, I'm a scientist in this field, this is hard to do, but that's what they claim to be able to do. And they're claiming that this will be operational by the 2030s. Tri-Alpha Energy, which is one of the three big companies that I mentioned that are billion dollar class experiments, are founded in 1998, and they have raised a lot of money. They aim to develop a practically commercially viable power source using a reverse field pinch. So a reverse field pinch generates a toroidal-shaped magnetic configuration, but unlike a tokamak, it has a relatively weak guide field, and indeed the field reverses at the edge of the machine. That's why it's called reverse field. And they aim to do this by using some plasma guns at either side, together with some large neutral beam injectors, which generate, or through primarily current drive, generate a reverse field pinch, which they claim will produce power in the early 2030s by either direct drive or indirect drive. And I mentioned indirect drive here. So Helion Energy is the third company of this, which is in the billion-dollar class experiment. So they're also using this field reverse configuration. What they're planning to do, however, is they've got a slightly different design. They have a design where they have these reverse field configurations generated at either edge. They then accelerate the RFP plasmas into the core, where it undergoes allegedly compression. The recoil of this, because it's proton-boron fusion, is meant to produce a change in the magnetic field, which induces a current, which can be then pulled out from the electrics of the system. So it's a bit like regenerative braking, except the electronics is much, much harder. They committed to providing electricity to Microsoft data centers from 2028. That's in 2 years' time. There's two companies in our region that it would be remiss not to mention, one of which is HB11. So this uses proton-boron reaction, but they're using this by non-thermal ignition by laser-driven plasma block acceleration. So their idea is to use petawatt-class lasers to generate very high field strengths. That certainly is the case. They're claiming to do this by non-thermal ignition, where it triggers an avalanche reaction of alpha particles. This was founded in 2017, building on the work of Heinrich Hohrer. It's raised about $30 million to date and claims to be commercially viable in the 2030s. The other experiment or project is over the ditch in Wellington, where they're using also proton-boron fusion. The reason why these companies are using this is because it's aneutronic. But as I said, the collision cross-section is much, much larger, much, much lower, so it's a much, much harder problem. They're using a levitated dipole device. So here you can see the dipole that's actually levitated. There are no physical supports here. It has an internal current supply, so it produces a large current flowing around it. This was founded in late 2021. It's raised about, up until very recently, $20 million US. They recently demonstrated experiments in this junior experiment. And most recently, as of last week, the New Zealand government invested $35 million into this activity, and the New Zealand Prime Minister ran a pulse, I think, yesterday. So little bro over the ditch is pouring large amounts of money into this space. What is Australia doing? I don't know. The UK approach to fusion. So the UK, the reason why I'm going to mention two other countries, the UK and China, because they have very ambitious programs and they're putting a lot of coordinated money into the space. So the UK has had a substantial program since the 1950s. They've hosted the Joint European Tourists. Since the early 90s, their domestic program has focused largely on this spherical tokamak device, which is more like this quad apple configuration, which was actually first demonstrated in Anstow by George Collins, even before the British did it in 1988. They have had a massive expansion in funding and program over the last 5 years. They have announced, or they've invested £650 million in this Fusion Futures program infrastructure for skills and industrial and commercial training activities. But most recently, in June last year, they announced £2.5 billion in Parliament for this ambitious spherical tokamak energy production device. So what is this? This is a prototype fusion energy plant which is meant to produce net electrical power to the grid. It's meant to have tritium self-sufficiency, so it will generate tritium by itself. It would have a maintainable reactor system and commercially relevant plant architecture. They've selected a site in West Burton, which is a former coal power station. And here's a schematic. I don't know whether you can see. There is a person here for reference, for scale. So unlike the tokamak that you've seen before, which is larger conventional aspect ratio, so it's bigger and fatter, this is thin and elongated. The other player that is putting a large amount of coordinated effort is China. So China has most recently been building this burning plasma experimental superconducting tokamak, or BEST. So this is a high-field tokamak under construction in Hefei, run by the Chinese Academy of Sciences. This again uses the DT cycle, conventional aspect. It's producing a high field strength on axis with about 5 megaamps of current. Its energy gain is between 1 and 5, so it's not as ambitious, but it is, the point is that once you get into this burning regime, you are approaching reactor-relevant regimes. So this is getting much, much closer to commercialization. They claim it will be operational by the end of 2027, and they've invested over $1 billion US. Money goes a lot further in China for lots of different reasons, some of which aren't so great, which is they don't pay their staff as well, but money does go a long way. They have a very ambitious timeline. Their construction began in 2023. They concluded the device, or they commenced the device assembly in May 2025, and they've already put in the vacuum vessel for housing the magnets. This builds on the success of the EAST program. So I've talked about the international activity. I've talked about what fusion is. I want to bring it back a little bit to Australia. So Australia was an early pioneer in this space. It co-discovered fusion science through the discovery of helium-3, tritium, and the DD reaction. So Mark Oliphant initiated much of this physics, plasma physics research at the ANU. There's been lots of innovations in that time. I won't go through the list. What I will do is call out a few things, one of which was the first tokamak outside of Russia. It wasn't actually intended to be a tokamak. It was intended to be a slow field pinch, but that was built at the ANU. A subsequent experiment, H1, and two notable icons, Sir Mark and also my mentor and former colleague, Professor Bob Dewar, who was responsible for much of the innovations in theory and understanding of toroidal magnetic confinement. Australia does have activity in fusion science, partly through the ANU, through theory and modelling, where I lead a group. There's also an activity in experimental science. Opal has, of course, the research reactor, but ANSTO has been heavily involved in championing fusion engagement in Australia, and I'm thankful for that. There is a growing activity at University of New South Wales, in particular in the Atomcraft project. I don't know whether anyone is here from Atomcraft, but they have an activity which is trying to build an undergraduate-led tokamak. There's HB11, which I've talked about. Curtin University has activity in atomic collision physics for neutral beam. University of Sydney has had traditionally a very strong presence in fusion. It now has an activity largely around plasma theory and mathematics, but it also has an emergent commercial activity, which is this hybrid electric and magnetic confinement device that has a virtual cathode, which is being led by Joe Kashan, who's in the audience today. There are several other companies, one of which is Storage Ring in Perth. I've introduced OpenStar, and Helicos, which is a fusion consultancy activity. There are lots of international collaborators. It's impossible in all of science to work without international engagement, especially true for toroidal magnetic confinement, because they are very big experiments with large amounts of money behind them. And if you really want to work in cutting-edge fusion science, it's a bit like particle physics. You need to work with experiments overseas. So in particle physics, you would work on the Large Hadron Collider and CERN. In the case of fusion, you would work with big experiments overseas. Is there an overlap with AUKUS? So that's a question that I have pondered over time, And indeed I've asked. So the person who leads the STEP activity was a former Royal Navy Rear Admiral responsible for nuclear submarine acquisition for the Royal Navy. He would know a thing or two about nuclear submarines, because that was his whole job, was to acquire them for the Royal Navy. So I had a chat with him, and also a UK AEA chief engineer who was also a Royal Navy engineer for 32 years, and they gave me a list of things that had an overlap. So a lot of these things, complex systems modelings, there are lots of things that are very complex systems approach. Fusion is a great example, but trying to integrate and operate a nuclear reactor in a confined space is another. There are lots of examples of where there is overlap. There is a second overlap, is that if you want to attract students to nuclear science, it's pretty hard to go past fusion. Fusion is a great magnet of students to nuclear science, because you're trying to do something altruistic. You're trying to help the planet. You're trying to make a game-changing technology. And you're doing it for good. You're not doing it to try and blow things up or create a large weapon. So it's a great pathway to attract students. And indeed, this is something which I think UNSW should be proud of. They have this activity where they're trying to build a student-led tokamak. They've had challenges over time, but I believe it's been they have a lot of enthusiastic students. And I don't think Patrick Burr, who is the person who is the academic responsible for this, is here tonight because he had another engagement. But certainly Joe Kashan has been involved with this, and there are people in the room who've worked on that project as well. So I want to come to a wrap-up. And so I've covered a bunch of different topics. I've introduced fusion. I've placed nuclear power, including fission, in context to global energy needs. I described different approaches to fusion power. I introduced and focused on the technology I think that's most likely to work, which is toroidal magnetic confinement. That's the one that has been the most investment to date and the most demonstrated progress. I introduced ITER, tokamak reactors and stellarators. I outlined the rise of the private sector and major UK and China programs, and I sketched Australia R&D past to present. What do I want people to take away from this presentation? Well, the first thing to do is fusion is very common in the universe. It's what is responsible for most of the energy production in the universe, and it's responsible for all of the formation of the elements. That great big thermonuclear furnace in the sky is why we're all here. Fusion on Earth, however, is hard, but if you could do it, the rewards are immense. So like fission, it is a very high energy density facility, but it doesn't have the same weapon proliferation potential. It doesn't also have the same large-scale radioactive waste problem. And the supply of fuel is largely infinite. So if you can make this work, it's very attractive. DT is hard. Proton boron is much harder. There is a good reason why the private companies are choosing this in the long term, and the reason is it's aneutronic, but the cross-section is 3 to 4 orders of magnitude lower at comparable temperatures. So if you can't do this, you're never going to be able to do that. Not in a magnetic confinement configuration. Large-scale utilities based on existing well-established but obsolete technologies like coal take roughly 10 years to build. So even if I wanted to build a power station right now, and it's based on coal, it's going to take me 10 years. So to say I'm going to produce power in 2 years is just preposterous. It's just not going to happen. It's make-believe. The possible exception is China, because China can invest a huge amount of money and it can bypass regulations. It can just drive things straight through without any form of Western regulatory control. The next step, ITER, is making progress. For the first time ever, it's ahead of schedule. DT operations are envisaged from 2039, but it's not a power plant. There are lots of things ITER won't do. My personal opinion is that I don't believe fusion will contribute to the grid before 2050, but this doesn't mean that Australia or the rest of the world shouldn't invest in it. Long-term technological solutions take time, and fusion is no exception. New configurations such as stellarators, new technologies such as high-temperature superconductors, advanced materials and AI do offer hope that fusion can be accelerated, and there's an opportunity to embrace this primary R&D program, these new configurations and new technologies, and the private sector to increase awareness and Australian participation in global fusion R&D. So as the chair introduced at the beginning, many years ago I formed the Australian EDA Forum to try and raise awareness of fusion science and ultimately for Australia to become engaged in EDA. We have succeeded in doing that. We haven't succeeded in the money that's associated with it, but we have succeeded in a cooperation agreement. And that's a feather in our cap. The next question is, how should we move forward? So I pondered this and asked some colleagues, and I think now is a good time to perhaps think about how the community self-assembly might rejuvenate in a different way. And I have a survey link, and I propose a follow-up meeting in March for those who might be interested in thinking about how the community might self-assemble to argue the case for not only additional fusion R&D, but also ask the question, how might we best combine some of our different skill sets to help advance fusion energy science. And so there's a QR code if you want to be able to participate in that survey, and I'll leave that on the front. Thank you for your time.